Okay, so let's take a look at today's lesson. Today's lesson we're going to look at particle motion again. We looked at particle motion several weeks ago, probably more over a month ago, with relation to derivatives. At that time, all we knew was how to take derivatives. And we talked about particle motion in that context. So I want to remind you what we did. It doesn't mean that we're going to not ever do that again. It's just we're going to have a different way also to do it. So when we had the derivative and we wanted to find displacement, we really actually needed the position to find displacement. We couldn't have just had the derivative back then. We would need the actual function. And to find displacement, if you recall, we just did end minus beginning of the actual position function. Remember that? So if we were let's just say we were looking to find, from say t equals 0 to t equals 3, of some kind of function. Let's say we were looking to find the displacement of, the particle that was moving. We would have done s of 3 minus s of 0, right? That would have given us our displacement. Remember that? That's what we would have done. When we had to find distance, if you recall, that was much more difficult because we know that the particle can move, right or left. And then when it moves left, it has it's negative. And so that would be a problem for us with distance. It would negate that part. So if you recall, we found the derivative, or we had it and we set it equal to 0 and we did a sign chart. Let's say in this case, let's say 2. Let's say that's what our sign chart was. Between 0 and 2, it was negative. The velocity was negative. And between 2 and 3, we were positive. And so what we did then is to find the distance, we took each section. Remember we did the absolute value of end minus beginning, like absolute value of s of 2 minus s of 0 plus. So absolute valuing it would negate, get rid of that negative. And we don't really have to do the absolute value of the second piece, but that's just what we did. So s of 3 minus s of 2. And that would have given us our distance, right? This gave us distance, and this gave us displacement. Okay, that's before we knew how to integrate. Are you with me? And you can still do that. That's still a viable technique. But now we know how to integrate, and we have more options available for us. We don't have to just rely on these two options. If we want to find displacement, what we can do is use this formula. Okay, so I would integrate from my beginning time to my ending time of my velocity. Integrating velocity gives me displacement. That's what it does. So let's look at this picture over here. If I want displacement, I would simply, collect or accumulate the area under the curve all the way across, going forward. If it was above the x-axis, it would be positive. If it was below the x-axis, it would have a negative sign. I would just accumulate the whole thing, right? And that would give me my displacement. Okay, so that's how to do it with integration. We would need, now this is important, we need velocity to do the integration for. Remember when we first started doing integration, I explained that aha moment I had when I'm like, how in the world can area be distance? Or we had, if this is our rate, see our velocity is here, our rate, and this is our time. The rate and the time is that product is our distance, that area is the distance. So with displacement, we treat, above the curve, under the curve, we just treat it as it is, positive, negative, positive. If we want distance, though, it becomes a little bit more difficult, just like without the integral, right? It was more difficult with just derivatives. It's a little bit more difficult. We actually have to do the absolute value of the velocity. That's what we have to do if we want distance. So looking at this graph right here, what I would have to do is I would have to alter this piece and force it to be positive if I wanted distance. So I would have to force it to be positive to get my distance traveled. And that's what this absolute value does. It's the absolute value of velocity, not of the result. So some students want to put the absolute value on the outside of here. That really doesn't do anything except for make our displacement positive. I would need to absolute value the actual velocity function and force it to be positive all the time. Okay, so that's how we would do distance with an integral. Again, we're integrating velocity. And actually, when we integrate just regular old velocity, that's displacement. When we integrate speed, so the absolute value of velocity is speed. When we integrate speed, we get distance. So those are two really important concepts for us to kind of absorb and really think about when that happens. So this is it in words. Integration velocity over time produces displacement. Integrating speed over time produces distance traveled. Okay. So these two formulas right here, those will certainly be on formula quizzes. Those are important formulas. We need to know how to find displacement using an integral. We need to know how to find distance using an integral. So those will be on formula quizzes. Okay, these aren't going to be on formula quizzes. Really, this is just highlighting a relationship, the relationship between velocity and position. If I integrate velocity, I get position. I mean, it's just talking about the relationship. That kind of is like common sense to us right now. If we integrate velocity, we're going to get position. If we integrate acceleration, we're going to get velocity. So these are formulas that they're not going to be on a formula quiz. They're just talking about trying to highlight the relationship between those types of functions. That's all. Okay, are we okay with that? This formula you would have probably memorized in, you know, pre-cal or algebra 2. This is on particle motion, this formula, where t equals 0 at the velocity at time t equals 0, so that's our s naught, our initial position, and v naught, our original velocity, initial velocity, would go here and here. You know, and that number, that a, remember that was acceleration due to gravity. Remember that from back when? Acceleration due to gravity. If we're in meters, it's 9.8 meters per second. If we're in feet, it's 32 feet per second squared.